You know that old heavy television that used to sit in the living room? Yeah, that one. Turns out, it wasn't just a piece of furniture. It was this incredible marvel of physics, a precision machine pulling off a tiny miracle 30 times every single second. So let's dive in and see how it actually worked.
Just picture it. You hit the power button. You hear that little click. Then that rising hum. You can feel the static crackling on the glass as it warms up. But what was really going on inside that heavy box? And that's the big question, right? It's a journey that starts with a single, invisible particle and ends with the movies and shows that pretty much defined a century. And it all has to begin inside a very, very empty space.
Okay, so the first piece of the puzzle you have to understand is the cathode ray tube itself. That giant, heavy glass bulb, it's not just there for looks. It is a carefully, perfectly constructed vacuum chamber.
And this is absolutely non-negotiable. See, if there was any air floating around in there, the little particles we're about to launch would just poof. They'd smash into air molecules and scatter everywhere. Game over. No vacuum, no picture. It is literally that simple. So with our empty stage all set, it's time to create our star player.
Way at the back of the tube, kind of hidden away in the neck, there's a little device called an electron gun. This is ground zero. This is where our journey begins, with the birth of a controlled stream of electrons.
The best way to think about it is like boiling water, but for metal. Seriously, a tiny filament heats up this piece of metal, called the cathode, and it gets so incredibly hot that electrons literally boil right off its surface. This creates a free-floating cloud of particles, all just waiting for the signal to go.
So how do you get that little cloud to move? Well, with a huge amount of voltage. A positively charged plate, the anode, acts like this super powerful magnet, just yanking that electron cloud forward and accelerating it to an insane speed, a pretty big fraction of the speed of light. That crackling sound you'd hear when the TV turned on? Yep, that's this massive high-voltage system kicking into gear. But here's the thing. A big, scattered cloud of electrons isn't going to draw a picture, right? It's useless. So it passes through a series of focusing electrodes. They act just like a lens, but they use electric fields to squeeze that cloud down into a single, unbelievably fine beam. Our particle has just been turned into a precision weapon.
All right, so now we have a high-speed, laser-focused beam of electrons hurtling down a vacuum tube. The next big problem? You gotta aim the thing. And for that, we turn to the awesome power of magnetism. Meet the deflection yoke. This set of copper coils is basically the steering wheel. By running really precise currents through them, you can create these powerful magnetic fields that can bend the path of the electron beam with pinpoint accuracy, pushing it up, down, left, or right, wherever it needs to go.
And this movement isn't random at all. The beam follows this super strict repeating pattern called a raster scan. Just look at this. It sweeps across one line, painting the picture, then it shuts off for a split second and snaps back. That's called the flyback. Then it drops down one line and does it all over again. It does this over and over, painting the whole screen so fast that to our eyes, it just looks like one solid, stable picture. Okay, so our electron has been created, accelerated, focused, and steered all over the place. Now it's time for the grand finale, reaching its destination at the front of the screen. This is where all that work finally turns into light. So the inside of that big glass screen, it's coated with these special chemicals called phosphors. And when our high-energy electron comes screaming in and smashes into one of these phosphor particles, it transfers all its energy, and that causes the phosphor to glow. Billions, and I mean billions of these tiny impacts happening every second create the light that makes up the picture you see. And look, a black and white TV was already a work of genius. But color? Whoa. That is a whole different level of complexity. Instead of just one electron gun, you need three. One for red, one for green, and one for blue. And the screen isn't just coated in one kind of phosphor, it's covered in millions of tiny individual dots of red, green, and blue phosphors. So this creates a massive engineering headache. You've got three separate beams firing at the same time. How on earth do you make sure the red beam only hits the tiny red dots and the green beam only hits the green dots millions of times a second without any mistakes? The solution is, well, it's just brilliant. It's an incredibly elegant piece of engineering called a shadow mask. It's this super thin metal sheet with millions of perfectly drilled tiny holes, and it sits right behind the screen. Now, because the three electron guns are angled just slightly differently, their beams all meet at a single hole in the mask. But as they pass through that hole, that angle makes them spread out again, just enough so that each beam can only hit its matching color dot.
It's just mechanical perfection. Of course, you can imagine this whole ballet would just be total chaos without perfect timing. Well, the TV signal itself actually has these invisible sync pulses built right in. They're the conductor of this whole electronic orchestra, telling the beam exactly when to sweep, when to fire, and even how bright it should be.
And the thing that powers this whole high-voltage circus, it's a component called the flyback transformer. It's what generates those tens of thousands of volts you need. And as a cool little side effect, it's the source of that iconic high-pitched whine that, if you're of a certain age, you can probably still hear in your head right now.
So, let's just step back for a second. We've seen all the crazy parts that make this thing work, but what do they really add up to? What is this machine really?
Let's recap. We are taking subatomic particles, launching them at incredible speeds inside a vacuum chamber, and then using powerful magnetic fields to steer them with pinpoint accuracy toward a target to create a specific reaction.
When you put it all together like that, you start to realize that for decades, this box sitting in millions of living rooms, it was something way more profound than just a way to watch cartoons.
That's right, that's what it was. Every single CRT television was a fully functional household particle accelerator, performing an incredibly complex physics experiment every single second it was turned on.
It really makes you wonder, doesn't it? As we move on to the next shiny thing, we tend to forget the absolute ingenuity behind the tech we replace. What other everyday objects from our past are just hiding a level of scientific brilliance that we've completely taken for granted?